Hello. So in this video, we're going to be going over techniques for finding limits. This video will only cover the first part of these notes in which we talk about properties of limits, and then in the next video, we will go over the different techniques to finding limits. So the first thing that we need to do is look at the theorems that we have to begin with here. So we have the theorem that involves the limit as x approaches a of any constant function. So here we have the limit as x approaches a of c is equal to c. And c and a are both constants. So if we look at the example, the limit as x approaches 2 of 6, this is just the function f of x equal to 6, which is a horizontal line. So the limit as x approaches any number, doesn't matter what number we have here, of a constant function is going to be that constant number itself. So our limit here is going to equal 6. And then we have the next part of the theorem, which is the limit as x approaches a of x is equal to a. So what this really implies is direct substitution. It means that whatever value we're taking the limit or we're approaching in the limit, all we really technically need to do is plug it into x. And so the function f of x equal to x is that diagonal line that goes through the origin. And we know that for every x value that we pick, for example, x is equal to 1, the y value is also going to be the same thing. So that's mainly where this comes from. This idea of being able to do direct substitution comes from the notion of this function and the way that its x's and y's work. So this means that if we're finding the limit as x approaches root 3 of the function x, then our answer will be root 3. Next, we have properties of limits. And basically what these are doing are taking those two basic theorems that we just talked about. So the limit as x approaches a of c equal to c, and the limit as x approaches a of x equal to a. And we're going to be able to do different combinations of those. So we have two different limit functions that we're going to use here to define the properties. We have the limit as x approaches c of any function f of x. Now, it doesn't necessarily have to be those functions that we just saw in the beginning. It could be any f of x. It could be something like x squared plus 1. Doesn't matter what it is. So the limit as x approaches c of f of x, and then we're going to have another function, g of x. But notice that we have the same approachment value. So x is approaching the same value, c. And that's important when it comes to applying these properties. The limits have to be, or their approaching values have to be the same. And then we have a and c, which are real numbers. So the first property is the sum property. That means if we have the sum of two different functions, so in this case, f of x and g of x are two different functions, but we are finding the limit as x approaches the same value for each of those functions, then we can go ahead and break those apart and find each of those limits separately. So for example, if we have the limit as x approaches 2 of x plus 1. So I'm starting with x plus 1 because those are really the two functions that we just saw in the theorem. And so what this property is saying is we can break it apart to the limit as x approaches 2 of x plus the limit as x approaches 2 of 1. So we took a function x plus 1 that was maybe a little bit more complicated, but we were able to use that sum property to break it down into two very simple limit examples. And now we can apply the theorem. So we know that the limit as x approaches 2 of x will have to equal 2, and then the limit as x approaches 2 of 1 will have to equal 1. So our solution here will be 2 plus 1, which means the limit will equal 3. So these properties allow us to take a function here and to break it down to then find the limit. Now, we've talked a lot about direct substitution already, and technically we could just do direct substitution, right? I could technically just take 2 and plug it into that only x value that I see there, and so that would give me 2 plus 1, which is 3. Obviously, it saves you all of this steps here. However, we're breaking down the properties and breaking down these functions so that we see where this actually comes from. It's really easy to just say direct substitution is the answer to everything, but we want to be able to understand where does it actually come from? Why is it that we can do direct substitution and that this works so well? So we're seeing the properties here, and also in some cases, we may not have all of the information that we would like to have in order to be able to just automatically do direct substitution. So in some cases, we may need to apply these properties because that's our only option that we have. So we'll see that later on, but we can see in this case, kind of taking a little more simpler example and really breaking it down to see where are these building blocks going, okay? We won't go through and do examples for all of these. We have a couple of examples at the bottom that we'll do together, but I'll kind of walk you through each of these properties here. We have the difference property, which is very similar, if not almost pretty much the same thing as the sum property. All the difference is instead of addition, we've turned it into subtraction. So you can see here, if you are taking the limit as x approaches some value of two functions that are being subtracted, you can take each of those limits separately. And also, technically, what I'd like to also kind of bring up that I don't think I mentioned is these work back and forth, right? It's an equal sign in the middle. So that means also if you have two different limit problems that you would like to subtract and they have the same x value that you are approaching, you could combine them technically and kind of go this route. So another thing I just want to bring up here in the many different useful ways that these properties will come in handy. So we have the difference property, and then we have the product property. So we know that product means multiplication. So it works that if you have two functions that are being multiplied, then you can break them apart and then just multiply their parts. So we will do an example here. If we have the limit as x goes to 3 of 2x, so this is really 2 times x, I could break it down and say the limit as x goes to 3 of 2 times the limit as x goes to 3 of x. And so the limit as x goes to 3 of 2 will give me 2 because the limit of any constant is the constant itself. And then I'm going to multiply that by 3 because this is just one of those direct substitutions. And so we get 6 as our solution here. And again, you can see we could have gotten that same solution if you just did direct substitution from the beginning, but we're just kind of showing how these properties work and why that direct substitution shortcut actually works. We can do one other one here that's very common is when we have something like x squared, right? Or any kind of polynomial type function. We could break it down, limit as x goes to -2 of x times the limit as x goes to -2 of x. And of course, that's just going to be -2 times -2, which is the same thing as just -2 squared. So as if you had just done direct substitution from the beginning, right? And just squared that and you would get 4. So just another example to show us how this product property will be applied when we do direct substitution into polynomials and all different kinds of functions. And we have the quotient property. So quotient means division. If we are taking the limit as x approaches c of two functions that are being divided, then we can take those limits separately, as long as this one, because we are talking about fractions, the limit as x goes to c of that bottom function, whatever is at the bottom, it cannot equal 0. So we can do something like the limit as x approaches 2 of x plus 1 divided by x minus 3. Something like this would work, because if I take the limit as x approaches 2 of the top and of the bottom and just go ahead and do that direct substitution to each of these, I would get 3 over -1, or in other words, -3. So something like this would work, but if we were to change this to a -2 instead, let me do that different color there, that would change this problem to having a 0 in the denominator, and that would be a problem because anything divided by 0 is undefined. So we cannot have a function in the denominator that gives us 0 when we take the limit. The next property is the constant multiple property. And so this says that if you are taking the limit as x approaches c of any function and you have a constant that is multiplying that function, you can always pull that constant out in front, take the limit of just that function, and then multiply it at the end. It makes things a lot more simplified. It's almost kind of like factoring out and then just kind of being able to multiply that to everything. So it's, if we had something like the limit as x approaches 3 of -4x squared. So instead of, doing, I mean, this one is pretty simple, direct substitution, but the idea is this constant multiple, we will pull it out in front and we'll have the limit as x approaches 3 of only x squared. And then once we find that limit, then we just multiply it by the -4. So in this case, we'll do direct substitution. That will give us 9 for the limit. And then -4 times 9 is -36. So that will be the solution there. The last property that we have here is the power property. And if you pay close attention here to the parentheses, we can see a little more clearly kind of what's going on here. So what this is saying is, let's say, for example, if we had the limit as x approaches 2, and we have some function f of x, and that function is being raised to some power. It could be just a natural number, it could be some kind of rational number. Let's say, for example, we have x squared, just to keep things really, really simple. So in this case, f of x would have to be x, and then x is being squared. And so what we could do, an option would be taking the limit as x approaches 2 of just x, and then squaring the whole solution. That's what this property is saying. If you see the way that the parentheses are written around here and where the power is at. And so to solve this, we would just use that theorem. The limit as x approaches 2 of x is going to be 2, and then 2 squared is 4. So we have a few examples here, and we're going to see if we can apply the properties to hopefully simplify it and bring it down to those kind of original properties that or theorems that we saw. So we have the limit as x approaches 1 of 2x plus 3 squared. So the first thing that I see is the square there. So what we can do is we can take that square and put it on the outside. So basically what we're doing is we're making the limit as simplified as we can. And then the next thing I notice is that we have the addition of two different functions there, 2x and 3. So I'm going to break that down into two different limits. We have the limit as x approaches 1 of 2x plus the limit as x approaches 1 of 3. And then that's all being squared. So I'm just taking each piece here and breaking it apart into two different limits, but they're both x approaching 1. And 3 is already super simplified there. 2x, I could go ahead and pull that 2 out, so it becomes 2 times the limit as x approaches 1. We're using the constant multiple property there, and then it just becomes x plus the limit as x goes to 1 of 3 all squared. So again, the point here is not to make things a lot easier, because as you can see, we're kind of expanding the problem. It would have been a lot easier to just plug 1 into that x and then to simplify, but we're seeing the building blocks. That's what we're trying to look for here. And we're trying to build the skills of how to apply these properties, because there are going to be some cases where we're going to need the properties. So we've got to make sure we can apply them. And so from here, all we've got to do is take both of those limits and then simplify from there. So we've got 2 times the limit as x approaches 1 will be 1, and the limit as x approaches 1 of 3 will be 3. And now that we've taken all the limits, we're just going to go ahead and simplify. That's going to be 2 plus 3 is 5, all squared will be 25 is our solution here. And let's move on to the next problem. We've got the limit as x approaches 8 of this rational function here. So the first thing that I see that's just like overwhelming this whole problem is the division, the quotient. So I'm going to break this down into two parts that are being divided. So up top, we've got the limit as x approaches 8 of x to the 2/3 minus 2 root x. And that's all divided by the limit as x approaches 8 of 3 plus 24 over x. So now we're taking the limit of two smaller pieces here, and we can actually keep breaking that down. At the top, we see that there's a difference property that we can apply, and at the bottom, we can apply the sum property. So this will give us the limit as x approaches 8 of x to the 2/3 minus the limit as x approaches 8 of 2 root x, all divided by the limit as x approaches 8 of 3 plus the limit as x approaches 8 of 24 divided by x. And so from here, we've got a lot of limits going on, but we can see that the functions within the limits are getting a lot smaller and kind of easier to find. We can go ahead and break it down even further. And for this first one, the limit as x approaches 8 of x and we can raise that all to the 2/3 power. And then we've got 2 root x, so that 2, I can bring that out in front. And this is going to be the limit as x goes to 8 of x. And since the square root of x is the same thing as x to the 1/2, I'm going to put that 1/2 there. And at the bottom here, the limit as x approaches 8 of 3 needs no further simplification other than actually finding the limit. And then we have the limit as x approaches 8 of 24. And we can divide that by the limit as x approaches 8 of x. So at this point, if you notice, you can see that we've simplified down to those 2 basic theorems that we started the beginning of the notes with, which is the first one here, the limit as x approaches 8 of x. So we know we just do direct substitution, that's going to be 8, and that's all raised to the 2/3 power. And then we have minus 2 times 8 to the 1/2 power, or if we want to, we could technically put in that root, make that the square root of 8. And in the bottom, we have the limit as x approaches 8 of 3, so that's going to equal 3. And plus 24 divided by 8. You've taken the limit as x approaches 8 of 24, it's just 24. The limit as x approaches 8 of x is 8. Now, all we've got to do is simplify. So I have 8 to the 2/3. I'm going to go ahead and cube root 8. That's going to be easier for me to do, and then square that value. And here, I'm going to simplify it under the root. So the square root of 8 is equal to 2 root 2. So this is going to become 4 root 2. And we've got 3 plus 3. 24 divided by 8 is 3. And we'll just keep simplifying. Cube root of 8 is 2. 2 squared is 4. We've got 4 minus root 2 up top. And 3 plus 3 is 6. So we have a 2 in common at the top, which will then simplify with that 6 and give us 2 minus 2 root 2, all divided by 3. So that's going to be our simplified solution here. As you can see, this was a very long process, but what I hope that you can recognize here is that the process helped us to break down this problem into those 2 basic theorems that we saw in the beginning. And so once we do just kind of focus in on direct substitution, always keep in mind where that came from. It came from those 2 main theorems and just kind of built right off of that. So this leads us to our substitution rules. So if we have a polynomial function, any polynomial function at all, polynomials are in this form here. If we're taking the limit as x approaches c of any polynomial, so c is any number, all you got to do is direct substitution. And the same thing is true for any rational functions. So rational functions are a polynomial divided by another polynomial. So you apply the same kind of rule. We're just going to do direct substitution. And in our next video, we're going to see how direct substitution works along with all of our other limit techniques.